All right, so today's notes are on section 6.3, which is on binomial expansion. We're actually going to take 2 days to do this lesson because we're going to learn 2 different methods for expanding binomials. And so before we actually get into the lesson, I'd like you to look at these 3. These are binomials because they have 2 terms, a and b, are the 2 separate terms. If we do a plus b to the first power, we obviously just get a plus b. And then a plus b to the second power, that is not a squared plus b squared. Okay, when we square a binomial, we need to multiply it by itself. And we have learned a couple of different ways, three different ways to do that. The book's method was using the distributive property. Then I also showed you how you could use FOIL, first, outer, inner, last. And then you could also do it using the box method where you would put a plus b and a plus b, and then do the multiplication and fill in all the blanks of the box. So you have 3 different methods. You should be comfortable with at least one of those. So go ahead and expand that one, and then after you do that one, then we're going to do a plus b cubed, which is a plus b times a plus b times a plus b. So what you're going to do then is take your answer from the previous problem, whatever you get here, you're going to put that in place of those 2, and then multiply by another a plus b. Okay, so go ahead and do that as a team, and make sure you're checking with each other along the way so that you have complete, simplified, and correct expansions for a plus b squared and a plus b cubed.
Third one, cube. A squared plus b squared plus ab squared. Plus 2ab.
Okay, Tanner, what did your group get for a plus b squared?
We got a squared plus 2ab plus b squared.
Okay, and that's good. And so then if we replace the first 2 parts, the product of the first 2 expressions here, we're going to just replace that with a squared plus 2ab plus b squared, and then we multiply by another a plus b. So again, you can use the distributive property for this, or you can put it in a box like this where you have a, b, and then Tanner's solution to the first one up here. And you can multiply those out and combine all the like terms and so on. And so when you do that, Molly, what do you get? What did your group come up with for a plus b cubed? Okay. Who's got that worked out? Adam?
A cubed plus b cubed plus 3a squared b plus 3ab squared.
Hello, I'm Mr. Dixon.
Hi.
How was your trip?
All right, so I wrote down Adam's answer here, but I actually put it in a different order than what he read because we want to recognize some patterns. And so Adam stated all the correct 3 terms, but I think he said a cubed plus b cubed first, and then he said 3ab squared and then 3a squared b. But I rearranged them, so all his terms are correct. The way that you can get those I showed over here in the box method on the right. When you're combining like terms, they're always on the diagonal, so you have a cubed is just by itself, and then these are a squared b terms. And so there's 2 there and 1 there, so altogether we have 3a squared b. And then these 2 terms are a b squared, and there's 1 there and 2 more there that are ab squared, so we have 3ab squared altogether. And then the b cubed here at the end gives us our last term. Okay? And so I want you to notice in just these 3, we could keep going with this and recognize more patterns if we did a plus b to the 4th, but we want to kind of get to recognizing some of the patterns that we have so far already. Okay? So in the first, in the a plus b, our coefficients are 1 and 1. I'm just going to fill those in here in red. 1 and 1 are our coefficients. So I'm going to put the 1 and the 1 there. And then the coefficients for a plus b squared are 1, 2, and 1, 1, 2, and 1, and then 1, 3, 3, 1. Okay, does anyone notice any patterns going on there? You may have seen this before, probably maybe in middle school you saw some of these numbers before in a diagram like this. We could even go back one and put a 1 at the top. If I before we did a plus b to the first, what if I did a plus b to the 0? That would just be 1, right? And so that would give us the top row. And see in this triangular pattern that's going down, we have 1s on the left and 1s on the right. Anyone notice patterns with the numbers in the middle? What do you notice? The 1 and the 1 in the second row, if I add those up, I get 2. If I add 1 and 2, I get 3. If I add 2 and 1, I get 3. And so if we continue this pattern, 1 and then 1 plus 3 is 4. 3 plus 4 is 6. 3 plus 1 is 4. And then it's going to end with a 1. And so this pattern creates what we know as Pascal's triangle. And so Pascal's triangle gives us the coefficients. See the 1, 3, 3, 1? Those were the coefficients that we got when we raised a plus b to the third power. So here, when we did a plus b to the third power, the row that has a 3 as its second number gave us the correct coefficients. When we did a plus b to the second power, this row gave us the coefficients 1, 2, 1, and the second number is a 2, and so on. So the second number in Pascal's triangle corresponds to the power that we're raising our binomial to. Okay, we're gonna expand Pascal's triangle out a little bit further. So far we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, and then we just did 1, 4, 6, 4, 1, which would be useful if we wanted to expand a plus b to the fourth power, because the second number is a 4. So we could actually do that real quick. It would go like this. So we'd have 1, 4, 6, 4, 1, and then look at the pattern with the degrees in Adam's answer. We started with a cubed, and then it went from a cubed to a squared, and then a to the first power, and then there was no a written in the last term, because that's a to the 0 power. Okay? And then the b's, there's a b to the 0 here that we don't see because b to the 0 is just 1. And then there's a b to the first power, a b to the second power, and a b to the third power. So the powers of a are starting high and decreasing. The powers of b are starting low and then climbing. And so if we do that here, this would have a to the fourth, and then 4 a cubed b to the first, and then 6 a squared b squared, and then 4 a to the first b cubed, and then the final term is going to be b to the fourth. So again, notice the a's started with the high power. The power of our binomial is the fourth power. So it goes 4, 3, 2, 1, 0. The powers of b go in the opposite direction. On the far right, we start with b to the fourth, then b cubed, b squared, b, and 0. Or counting down from the left, we could just say b to the 0, then first, second, third, and fourth. Okay? So that's how Pascal's triangle is going to give us the coefficients. What I'd like you to do is go ahead and expand this out until your second number is a 7. Okay? Keep expanding Pascal's triangle until you get to the row that has a 7 as the second number. Okay, so they always start with a 1, and then we add the two adjacent numbers to get the number that goes right underneath them. So 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then we finish with a 1. And if we just repeat that pattern, then it would go 1, 6, 15, 20, 15, 6, 1, and then 1, 7, 21, 35, 35, 21, 7, and 1. And that pattern can just continue as long as you want, as far as you want, so that you get to the row that you need for any expansion. So this one would allow us to raise a binomial to the 7th power because the second number is a 7. Okay, and so now we're going to use Pascal's triangle to expand some binomials. So for our first example, we're going to do x plus 2 to the 5th power. Go ahead and copy this down, and then I'll work through this example with you. Okay, now since this is a 5th degree binomial, we're going to use the row that has a 5 as the second number. Okay? And so I'm going to start with the powers of x and count down. So I know it's going to start with an x to the 5th. Now, please work in pencil and also leave lots of space in between. So I'm going to start with x to the 5th, and then I'm going to put plus blank x to the 4th, plus blank x cubed, leaving a lot of space in between, x squared, then x, and then x to the 0 power. Okay? And then now I'm going to do the 2's. We'll start with 2 to the 0, which is 1, and then this one's going to have 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, and 2 to the 5th. So the first term of the binomial starts with the 5th power and counts down. The second part of the second term of the binomial starts with a power of 0 and counts up. So this is, we could fill in a 2 to the 0 here if we wanted to complete the pattern. 2 to the 0, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, and we know when we're done when we get to 2 to the 5th power because that's the highest power we're going to have. Okay? And now I'm going to look at Pascal's triangle for the coefficients. So the coefficients are going to come from this row. 1, 5, 10, 10, 5, 1. Okay, so those numbers gave us those numbers from Pascal's triangle. The 5th row, even though that's really the 6th row in the table, if you in Pascal's triangle, we're going to refer to that as the 5th row. Okay, the top row being the 0th row, because that's what we use when we raise something to the 0 power. Okay, and so now we just need to simplify. And so this first term is going to just simplify to x to the 5th. The second term, look at the numerical parts. We have a 5 times a 2, and so that's 10 x to the 4th. And then we have 10 times 2 to the 2nd, which is 10 times 4, or 40, x cubed. And then we have 10 times 2 cubed, which is 8. 10 times 8 is 80, x squared. And then we have 5 times 2 to the 4th, which is also 80, because that's 5 times 16, 80x, and then plus 2 to the 5th, which is 32. Okay, so then that is our final simplified expansion. Now that might seem like a long process to you, but if you want to compare that to expanding x plus 2 this way, if you tried doing this the way we did the first 3 examples today, I think you'd realize that expanding that out using the FOIL method or the box method 5 times is going to get pretty cumbersome and has a lot of opportunity for you to make errors. And so Pascal's triangle is a way to simplify that process a little bit so that we get the coefficients and then just use the patterns of the degrees. Okay? Now, as I was writing these down in this row, before we simplified, did anyone notice any patterns with the powers? I have x to the 5th and 2 to the 0, then I have x to the 4th and 2 to the 1st. Okay, what did you notice, Robin?
With the powers, they always add up to the first coefficient. For example, if 3 plus 2 is 5. Or not coefficient, the power of whatever it's called.
The exponents?
Yes.
Add up? Yes, so the exponents always add up to, in this case, 5, because 5 plus 0 is 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, 4 and 1 is 5, and 5 plus, we could fill in an x to the 0 if we wanted to complete that pattern. 5 plus 0 is also 5. So those will always match the degree of the binomial that we have in the original problem. Okay? So that's a good way you can error check yourself to make sure all of your degrees are correct, is at each step they should always add up to the degree of the original binomial. Okay? I'm going to do B with you also, or at least I'm going to start it with you because I want to make sure you understand how to do this when there are other expressions involved. Okay? And this time I'm going to write down Pascal's triangle, the numbers from Pascal's triangle first. And so Pascal's triangle, the row that has a 6 in it is 1, 6, 15, 20, 15, 6, 1. So I'm going to try to spread those across my paper. One, 6, 15, what was the next number? 20, and then 15, 6, and 1. Okay? Now we have to be really careful with parentheses here, because this isn't, a lot of you may write this by mistake, 3x to the 6th, when it's actually the quantity of 3x to the 6th. Now that's going to make a huge difference in your answer. So make sure you put that in parentheses. Then we're going to have 3x to the 5th and negative 1 to the 1st. Now notice how I brought the negative sign with the 1. Then this one's going to have 3x to the 4th, negative 1 to the 2nd, because the powers have to add up to 6 in this case. Go ahead and see if you can fill in the rest of the parentheses. So we're going to continue with that pattern, 3x to the 3rd, negative 1 to the 3rd, and then 3x squared, negative 1 to the 4th, 3x to the 1st power, negative 1 to the 5th power, and then 3x to the 0 and negative 1 to the 6th. Now, we should double check, make sure our exponents always add up to, in this case, they should add up to 6. So we have 5 and 1, 4 and 2, 3 and 3, 2 and 4, 1 and 5, 0 and 6. Those all add up to 6. And so now we're ready to simplify. And so we need 3 to the 6th power for the first one. Okay, so 3 to the 6th is 729, so this is going to be 729x to the 6th. And then we need, for this one, we need 3 to the 5th times 6. So if I do 3 to the 5th times 6, that's 1458. And notice that it's negative 1 to the first power, which is going to be negative 1, so I'm going to change this to a subtraction sign. Okay, so it's minus 1458x to the 5th. For the next one, we're going to have 15 times 3 to the 4th. And I don't really need a calculator to do it, but what we're doing is negative 1 squared. And so that turns out to be 1215 x to the 4th, and so on. Go ahead and simplify the rest on your own. Yeah. All right, so let's see, Caitlin, what'd you get for the next term? Okay, and then Giovanni, the next term? 135x squared, is that what you said? Okay. And Kenneth, the next one?
Negative 18x.
And then the last one, what's that going to be, Logan?
The plus 1.
Plus 1. Okay. Are there any terms there that you got a different answer? Any that you disagree with or want an explanation on how we got those numbers? Everyone agrees with those? Okay. All right. Go ahead and try these last two, C and D, using Pascal's triangle. All right, so let's go ahead and take a look. You can check your answers on those two. And let me know if there's any particular term that you want to see how I got the coefficient for that term. For part C, make sure that your signs are alternating. So the first term's positive, second term's negative, positive, negative, positive. Because it's negative 5 that we're raising to the different powers. So whenever it's an odd power, you're going to get a negative coefficient.
How did you get the x to the 4th one?
For C or D.
You don't put that D.
Okay. So to get this term, guys, to get this term with x to the 4th, we would, using Pascal's triangle, it's going to have, let's see, it's going to be 1, 6, 15, and so this is going to have a 15 in front, and then it's going to be 3x to the 4th power, which means the 2 is going to have to be raised to the 2nd power. And so then on your calculator you can do 15 times 3 to the 4th power times 2 to the 2nd power. And that is 4,860 x to the 4th. Okay, other questions on those?